Okay, so hi, my name is Dr. Tim Arnett. I'm one of the organizers for XFC this year, and today I'm going to be talking about fuzzy systems, both fuzzy logic and then an extension of that, which is fuzzy control systems or fuzzy inference systems, which utilize fuzzy logic in order to provide input mappings to outputs. These slides were generously shared by Professor Kelly Cohen at the University of Cincinnati. Some of these were from a class that he teaches on fuzzy systems, which is a dual level course that here at UC. So I'm going to go over some high level aspects of fuzzy and why it's useful, and then also talk about some of the more specific operations that occur within fuzzy systems. So this graphic is showing quote unquote state-of-the-art solutions for a number of different problems in both machine learning and optimization. And under the umbrella of optimization, we have several algorithms under heuristic methods, which include things like genetic algorithms, simulated annealing, et cetera, and also expert systems, which can be based on binary logic, like a typical or a classical decision tree, or fuzzy logic, which is what our focus is. These color-coded boxes below each of these represent that method's capabilities with respect to optimality, time, scalability, and robustness. And then we have these color codings for good, medium, and bad. I disagree slightly with some of these. These were created by Dr. Elad Kabelovich, formerly at UC, now at MathWorks. But what I want to draw attention to is some of the capabilities of fuzzy logic. You can see that for optimality, it's medium. And really, though, this is a function of the number of parameters in your system, because fuzzy systems, depending on the operations that occur, but generally they are what are called universal approximators. So it can approximate any continuous function to any arbitrary degree of accuracy if you just increase the number of parameters until you get the accuracy that you want. There's a trade-off with that, though, and that is the other block relating to scalability, which is that fuzzy inference systems do not scale well as you increase the number of inputs. And there's a specific reason for that, but we'll talk about that more later. However, as far as time, evaluation time and potentially creation of fuzzy logic-based systems is pretty fast. And one of the hallmarks of fuzzy is its robustness to noise. That is an extremely powerful part of fuzzy. We have some other methods that we see over here. These are sort of, this is an optimization protocol for reinforcement learning. Neural networks are another function approximator and the primary rival of fuzzy inference systems, I would say, and one of the most popular architectures out there in machine learning. However, one issue with neural networks that we've seen time and time again is that they're not very robust. They tend to be brittle as compared to fuzzy systems on similar problems. So to get more into what fuzzy logic actually is, we're going to start talking about your work week and the weekend. And if you're trying to categorize the days of a weekend as, the days of the week as being part of a weekend, either yes or no, let's say that you had Saturday. I think everybody would agree that Saturday is completely a weekend day. So we can just say that yes, it's unequivocal, it's true. Yes, that is a weekend day. And if you think about Tuesday and you wanted to say, is that a weekend day? Obviously, no. It's surrounded by weekdays. Yeah, it's completely not a weekend day. But then what do you say about Friday? Is Friday a weekend day? Some people might say yes, completely. Somebody would say no, it still counts as a weekday, not a weekend day. But really, it's somewhere in between because it has aspects of both being part of the work week and being part of the weekend. So it's not completely, it doesn't capture all the information just to call it yes or no for one or the other. And so there may be some score in between that you would like to assign to it, where you'd say 0.8, well, it is mostly a weekend day based on the aspect that, you have people leaving work early, you have people going out that night, doing things like that. But not completely. You still have to work that day, at least for the most part of the day. And what about Sunday? Well, sort of the same situation, but in reverse, where, yeah, the early part of the day is absolutely a weekend day. But that evening, you're getting prepped for the work week, you're going to bed earlier, all these things. And so it's still a weekend day, but not as much. It's not as clear cut as Saturday is. And so obviously binary logic, just one or zero or yes or no, doesn't fully encapsulate that information. And so fuzzy allows us to extend that and give different values for the truth of that statement. This is a graphical representation of that. So if we have these bars representing the amount of weekendness of a particular day, you can see that Saturday and Sunday, classically, we would say that yes, those are both weekend days, everything else is a weekday. But then we can extend this with fuzzy by saying that, well, we can assign these values that are not strictly 0 or 1, somewhere in between, that more accurately represents the weekendness of that day. So Thursday, has a little bit. People like to do things on Thursday night. Friday, quite a bit. Saturday, full. Sunday, not quite full. Monday, obviously not a weekend day at all. And then this is a continuous plot. Well, in this case, there are discontinuities because of the binary logic representation. But then we can have this smooth continuum representing the fuzzified version of this, where what we would call this is a membership function, because this curve is a function that describes the membership of a day within the weekendness set. And along that curve, you can then calculate how much weekendness a particular day has. And yeah, and so to more accurately reflect this noisy data set, or this noisy input space that we have, where things aren't just crisp, going to 0 or 1, we can say that the truth of these is more accurately described by this type of curve. We can do a similar thing with seasons of the year. We do have these dates on the calendar where spring, summer, fall, winter officially start. So you can classify it this way, but that if you're trying to do something like weather prediction, it doesn't necessarily help you that much to have this hard cutoff. And so you want a more smooth transition between them, and you definitely get overlap, in between the seasons. There's not a single date where spring stops and summer starts, and then you all of a sudden have no more rain and bright blue skies and 95-degree weather. Although here in Ohio maybe that does happen, but generally we like to consider there's an overlap between these, and so a date in early May, you're going to have contributions from behaviors from both spring and summer. And similarly, what we're seeing right now for fall and summer, we're on the trailing edge of summer, but we're still getting quite a bit of contribution weather-wise from what we would consider summer to be. One of the leading authors and publishers of papers in the world of fuzzy is Bart Cosko, and he's put out a number of articles on fuzzy thinking, and he's a proponent of it and what he means by fuzzy thinking is assigning these gradations of membership in sets as opposed to binary. And he argues that this is a better way to do things because, a human reasons with scant evidence and vague concepts, but we're still able to make decisions based on that. Rules of thumb, tentative facts, hunches, beliefs, estimates, and guesses. And natural selection evolved with this uncertain cognitive calculus. And basically what that means is that populations evolved to deal with noisy and large amounts of information very quickly in a quick and dirty sort of way to get a best estimate for what to do, and how to consider things without needing exact and precise measurements. And yeah, everybody uses fuzzy calculus to run our lives, careers, etc. Most people aren't calculating every little aspect of their day, and most of the times that's not really useful, both from a time aspect and the benefit of doing so. And while we employ the products of exact science and as decision aid tools, the final control remains fuzzy. And here we're talking about humans, by the way. I want to make that clear. So precision versus significance. This is a popular graphic showing this. And this is what we were talking about with fuzzy thinking, which is if, this weight or whatever it is falling towards a person, and obviously it's going to harm them quite a bit, or if not kill them, and you want to make sure that they have the information they need in order to avoid this situation, you're not going to say, hey, a 1,500 kilogram mass is approaching your head at 45.3 meters per second. That's not that useful. That won't convey the information. I mean, it may convey the information, but it's too precise. It's not adding additional information for them to help them make a decision. In fact, it's probably doing the opposite because they have to consider all these things when you could yell, look out, or get out of the way, or jump, or something, because that is the more relevant information for them in that at that time. And so it's always a trade-off between the information that you need and the precision that you need in that information to make good decisions. And most of the time, in the situations we're talking about where you have noisy situations or lack of precision, fuzzy is an important tool. These are just a few statements from notable people about fuzzy and precision. Matisse said precision is not truth. DuBose said sometimes the more measurable drives out the most important. That can definitely happen. People, if something can be measured easily, it tends to get used more often than not. And Einstein famously said, so far as the laws of mathematics refer to reality, they are not certain. And so far as they are certain, they do not refer to reality. And then Lottie-Zada, who is the father of fuzzy logic, he was the creator of fuzzy logic back in the 60s, stated, as complexity arises, precise statements lose meaning and meaningful statements lose precision. And that really deals with this inference that we'll talk about in a minute, where you are inferring these general rules for systems from either from data or from some other method to generate meaningful outputs. Like I just mentioned, Professor Lottie-Zada invented fuzzy logic in 1965, and the idea was that it allows the computer to model the real world the same way that people do, as far as shades of gray and for decision making. When people make decisions, a lot of times they're doing something very similar with their thought processes as what we'll see in fuzzy inference systems, but they're doing it in sort of a quick and dirty and implicit way. But they're definitely not writing down they're not trying to quantify every aspect directly and then calculating some exact value. And because most of the times that's also not useful. But fuzzy logic also has the ability to deal with situations in which one may not be able to make those sharp distinctions between the boundaries of application or rules or constraints. That is a big thing, especially when you have extremely complex or noisy models in the AI and machine learning space, as we'll see. That's extremely beneficial. A fuzzy logic system is unique in that it's able to simultaneously handle numerical data as well as linguistic knowledge. This is a big thing. We'll see what we mean by linguistic knowledge in later slides, but as you guys will be focusing on explainability in your solutions, having these linguistic representations is important. is a nonlinear mapping from input data to output. So it's still mapping numbers into numbers. You can represent things linguistically in between, but you're still taking input values and mapping them to output values. Typically in the real space, but what that represents is this is a function. Fuzzy systems are functions. And fuzzy set theory and fuzzy logic establish the specifics of these nonlinear mappings. So traditional crystal logic, we've already talked about this. I'm not gonna. Yeah, so some of the motivations behind fuzzy logic, though, they alleviate difficulties in developing and analyzing complex systems encountered by conventional mathematical tools. One area where you see this quite a bit is in control theory. The classical control theory and even modern control is typically based on linear systems or linearized systems. Whereas nonlinear control offers you quite a bit of benefit at the expense of being able to mathematically analyze their behavior in a lot of situations. And fuzzy is particularly good at being able to be implemented in these systems with little or no domain knowledge. And that can come from both human reasoning or machine learning protocols. But also another thing is, observing that human reasoning can utilize concepts and knowledge that do not have well-defined sharp boundaries. In a lot of cases, if we're going from expert knowledge, you may have, an operator that describes something as good or bad or, very good, very bad. And what that actually means within the context of the system is not typically easily encapsulated by some crisp value. Sometimes you can go through, you can do interval methods, but fuzzy even extends that. So not only an interval, but now also some description of the membership beyond that. So I'm actually going to skip that slide because we've already talked about precision. And again, fuzziness is beneficial for complex systems that are difficult or impossible to model, especially systems with very noisy states, and those distributions are hard to model. Systems controlled by human experts or systems that use human observations as inputs. Humans deal in natural language, which is extremely vague most of the time and messy, and that is where fuzzy thrives, is still combining those with, if necessary, with actual numerical values. And again, systems that are naturally vague, behavioral and social sciences. Sorry about that. There are a number of papers out there demonstrating the efficacy of fuzzy logic and fuzzy set theory in some of the softer sciences, because we have human developed descriptors, but then we want to actually reason about them in some way. I would like to highlight something, which is that fuzzy logic is not probability. They're often confused, and even if you can notionally represent a fuzzy system as, or at least its output as a probability, which you can do, fuzzy logic and probability are still not the same thing. They do both offer degrees of membership, both degrees of membership in fuzzy sets and probabilities are numbers between 0 and 1. So people may think that they are the same thing or interchangeable when really they're not, because probability is the likelihood that something will happen in the future, and by that something meaning you will be in a set or not, whereas fuzzy is grading something that has already happened. It measures the ambiguity of events that have already occurred. So it's not something happening in the future. Now, there are people that have worked on the similarities and relationships even more between probability and fuzzy, and there are a number of papers out there that I encourage you to read, but the easiest thing to remember is that at the basic level, they are not the same. They're describing two different things. These are some milestones in early fuzzy history. It was introduced in 1965. The first fuzzy logic controller was in 1974. A lot of these were created from expert knowledge. You know, they would have some operator for some industrial system, whatever it is, and they could create rules for that system, a controller, from that expert knowledge, because they had these linguistic representations of what the system should do, and they could encode that as a fuzzy controller. That was really sort of uh, the state of the art of fuzzy control development until much later on they started optimizing fuzzy controllers with machine learning processes. And you can see in the early 90s, we started getting rule learning by neural nets. We got hierarchical controllers to make the space smaller. And then we also got combinations of optimization algorithms with fuzzies, such as backpropagation, genetic algorithms, things like that, which really expanded the efficacy of fuzzy systems for larger systems. So again, crisp and fuzzy sets, this is a more definitive example, but this is one that gets shown quite a bit, which is a person being tall or not. So this is a crisp set, or a Boolean set, showing if somebody is tall or short. And so we're saying that if anybody is 180 centimeters or taller, they are tall. Just, they are tall. They're a tall person. And if you're anywhere below that, so below 180, you are short. And that's it. There's no other distinction. However, we can have a fuzzy set with this continuous curve that shows how tall you are exactly, and the contributions for that are both short and tall. In this case, we only have one fuzzy set, so the remaining will be in the other. So if we say, let's say you're 180 centimeters tall, here that would put you at about 74% tall and 24% short. So you're now not completely tall or completely short. You now have contributions from both. And although this is a nice representation that is probably more true to, or a more accurate representation of a person's tallness, you may be thinking, well, okay, but what do we do with that information? Well, we'll see in a little bit that, based on contributions from both of these sets, tall and short, we can then create some sort of decision that's based on both of those. But yeah, so membership functions, this embodies the mathematical representation of a membership in a fuzzy set. So the curve that we just saw, this may look somewhat like a sigmoid curve, but there are all sorts of different shapes. We've seen triangular. You'll see some other ones that are, Gaussian, trapezoidal, maybe even singleton if you're doing something very specialized. And the notation used for a fuzzy set is a set symbol with a tilde underscore. This is not as common, I would say, in the literature, but you will see mu being used quite a bit for representing the membership value. But anyway, what this notation is saying right here is this is the degree of membership, mu, of element x in fuzzy set A. So it's a value on the unit interval between 0 and 1 that measures the degree to which element x belongs to fuzzy set A. These are some other representations. We see a singleton right here. We see a triangular membership function. We see a trapezoidal. And this is an interval, more closely related to a crisp set. Again, these are some more common membership functions you might see. And in fact, these, I believe, are directly from the MATLAB toolbox for fuzzy. And so this one by default has a bunch of different options you can pick. You can also define your own. And you can do this in a lot of other modules as well, including ones for Python. But typically you'll see triangular, trapezoidal, I'm so sorry, Gaussian, another type of Gaussian, a Bell, and then they also have some, I believe, sinusoidal based ones, sigmoid, etc. And really the type of membership function depends on your problem and the properties that you're looking for. A lot of times you'll see triangular, trapezoidal, or Gaussian because of the properties that they provide. Triangular and trapezoidal tend to be some of the best for learning either clustering or some sort of interpolation type problem. And Gaussian you tend to see quite a bit in continuous control problems, but they all have their uses. And I actually encourage you guys to not limit yourself to a single membership function when you're designing your systems. Again, these are some more examples of membership function shapes. So we've already talked about membership functions, singular membership functions, but what happens when we have multiple? And so this is a representation of, again, a similar problem with where you're describing a person's tallness. And so we have their height in centimeters, and we're now going to put them in a bunch of different sets based on where they fall in that range, described by 3 different membership functions. So we have a membership function representing short, medium, and tall. And as these are trapezoidal, there are places where they will have full membership in a particular set. So we can see below here, which we'll say is, I don't know, approximately 157, something like that. They're short. They're just always short. And that's the same, between about 162 and 172, we're going to say that they're just medium. And then again, above about 177 or 180, they're just tall. But in between, we can see that there are contributions. There's this overlap from medium and tall and short and medium. And so if you're in between these ranges, you're going to get contributions from both short and medium, and here medium and tall. We can also do this with a bunch of other things like healthy or less healthy, or even unhealthy. If we have some metric that's giving us a health index for a person, we can describe them being healthy or not. Another place you might see this typically is temperature as described by humans. That's a common example that you'll see. I believe the MATLAB toolbox has an example dealing with that. But again, what we're focusing on here, the concept I want to drive home is this overlap, because that overlap is when you're getting contributions from multiple active fuzzy sets. This is just a graphical representation of Boolean and fuzzy logic operations. So set operations, set operations, this is showing the total A and B. This is showing their A and B, the conjunction. And then the last one, or sorry, the first one is the union, A or B. And then the last one is the complement of that, so the opposite of A or B, not A or B. Similar things happen in fuzzy, where we can see if we have this description, the input space described by these fuzzy sets, we can do similar things with union, intersection, and complement. There's also another term for this called T-norms, which I encourage you to look up in the literature if you're more interested, but it's describing these operations, but in a more mathematically rigorous way. So one of these T-norms for fuzzy union, if we have A union with B, is this, just the max function. So you're simply taking the maximum of those 2 membership values. So if we go back one slide and we're looking at, well, we'll see some more concrete examples, but if we're looking at this situation, we would be taking the maximum value. So let's say we fell right here along the x-axis. We would be at about right here in the A set and about right here in the B set. Since we're taking the maximum, we would take the value here for A, and then we are going to use that further down the line for our inferencing operations. Similarly, the intersection, if it's sorry, that's or, not and. I misspoke. For intersection, we'd be taking the minimum. So instead of that situation, we'd be taking the minimum, which would be the value for B. And then, of course, the complement is simply 1 minus the value, which can be useful if you're trying to simplify your operations. These are just another graphical representation of these with and, or, and not. These are from the MATLAB Fuzzy Toolbox, which also has a lot of helpful documentation. Okay, so these were the slides that were mainly focused on fuzzy logic. Next up, we have fuzzy inference systems, which is using fuzzy logic to perform that input to output mapping. But to review, fuzzy logic is conceptually easy to understand. It allows decision making with estimated values under incomplete and uncertain information. That's one of the big things. It is a universal approximator given certain properties. I will say the vast majority of fuzzy systems and their configurations are universal approximators, but it is possible to create some that are not. And they've been successfully applied in many fields: automatic control, data classification, etc. But really where we want to focus from here on out is fuzzy logic controllers or fuzzy inference systems. And this is a general block diagram of a fuzzy logic system. So it's this in this dashed box. We get some inputs in. It goes through some fuzzification interface. So it gets fuzzified, meaning you evaluate it in your membership functions and you get your membership values out. That then goes to your rule base. So this describes all of your inferencing. So the associations of your input fuzzy sets and your output fuzzy sets. So then you have a bunch of output fuzzy sets that are activated, and then you have to resolve those into a value somehow. So then that is what the defuzzification interface does. And this outputs a crisp value. That's what comes out right here. So you're inputting a bunch of crisp values and you're getting crisp values on the output side. In this overall graphic, we're showing a feedback system. So this goes into some plant or system, which then you get outputs from, and then this is fed back through sensors, and that can go back into your inputs. Generally, though, the fuzzy inference system is just this block. So that's what we'll be talking about a bit more. So control using fuzzy logic. The basic idea is you write control actions as rules. The difference between this and like a typical if-then statement is that we have that overlap and fuzziness involved. And you can see this like, in standard logic, let's say that we had this a heating system, and we have a simple rule that just says if temperature is less than 68 degrees, I'm sorry, I'm having cursor issues, then turn the heater on. That simple. And that means that if it goes below 68 degrees, the heater will always be on, and apparently the heater will just be on full blast, full power. Conversely, with fuzzy logic, we could say something like, if it's very cold, then more heat. And those fuzzy statements, those linguistic representations, are representative of fuzzy sets. And those fuzzy sets then determine what your actions are through those processes I just mentioned. So you can have these vague, imprecise rules that then result in some actual control action. Again, this is the flow diagram. So we have a sensor giving us input information that goes through the fuzzification process. This is simply another input set of fuzzy membership functions. So that's what you see here. You see, well, I don't know what L means. Probably negative large, and then negative small, 0, positive small, positive large. That gets passed through your inference engine, which uses the rules to then map those to output sets, and you get some aggregate, and then you defuzzify, and then you get an actual output. So we'll see how this is done in a second. But what this also does is you can see that this is very discontinuous. You have a hard cutoff. This also allows you to do things more gradually and smoothing of your control actions. So rules reflect expert decisions, although you can derive these rules directly from data. You can also learn them through processes like reinforcement learning, which is what you guys care about. This next bullet, in a fuzzy system, all rules fire to some extent. That's not always the case, actually. However, if in your situation you have rules not firing, that does tell you something. That means that essentially you have additional membership functions in your input spaces that are not useful because those rules are not firing. And if it's not possible at all for them to fire, then yeah, there's a structure issue. But yeah, you do want all of your rules to fire to some extent at some point. Again, a fuzzy rule can be defined as a conditional statement in the form if then. So if a car runs very fast, then the brake distance is long, even though brake is misspelled. And these if then statements are similar to the classical rules, but these mean something very specific with respect to the fuzzy set operations that occur. So this is showing the entire process of the input values, the inferencing, and then the output values. So let's go through this step by step. So we're getting input values for both X and Y. That's what these bars are. And we have input sets for X and Y. This is just showing one of the membership functions that is active in X, so one of the ones that this bar falls in. And this is showing one of the ones in Y. So this represents a single rule that is firing. And so this single rule is saying if X is whatever this membership function is, and Y is whatever this one is, then whatever this output membership function is. Notice that this is a different set of fuzzy sets. This is Z, our output. So if X is this and Y is this, then fire this output membership function with this strength. And this strength is determined by that AND operation that we saw. So it's taking the minimum, which by the way is called the minimum T norm of X and Y. And that's where we get this final shape for that rule that it's firing. Now, because we're following, our inputs fall in multiple different membership functions because they overlap, we're going to have multiple rules active. In this case, we're only showing two rules. But let's say that we have another membership function in X that it falls within, and another in Y that it falls within. And you can see the membership values are different, even though they look like they're the same, kind of, on this graphic. They are shifted, so we have different membership values. And in this case, we have, again, the minimum is Y, but we're taking the minimum of these two memberships. It's a bit hard to see this lower dashed line. And then we have an associated output membership function, which is different from this one, and our rule strength, and that determines that shape. So we have all of our rules. That was our inferencing. Now we're going to our defuzzification protocol, because now we have these active weird output shapes, these truncated triangles. So we have these trapezoids which overlap themselves, and we have to resolve this into some output value. So typically how that is done is by either taking the centroid or an approximation of the centroid. But there's quite a few different defuzzification options. This on the right is showing an example of using centroid or approximate centroid. And so you can see this is where the output would be because you're taking the centroid with respect to this dimension. We don't necessarily care about this dimension. And that is our output value, our final output value. So again, this is another example showing the entire process. We get some measurement coming in. In this case, it's for some temperature control system that says, if the temperature is within these, then do something to change the temperature. So, if temperature is cold, then the valve is open. If temperature is warm, the valve is off, or sorry, valve is half. If temp is hot, then the valve is closed. And so what we can see though is our input value only falls within cold and warm. We don't have any membership in hot. And the membership values it has is 0.7 in cold and 0.2 in warm. Note that these do not add up to 1. That is not a strict requirement for fuzzy controllers. You can have membership that does not equal 1 everywhere. That is allowed for fuzzy controllers, even if you miss out on some nice properties due to that. However, so what this is saying then is we're going to go to our inference engine for these two fuzzy sets, warm and cold. And we know this rule says, well, if temp is cold, then valve is open. And so these are our output membership functions, by the way. They look similar to our inputs. They don't have to. They can be whatever they want to be. But if temp is cold, then valve is open. So we know we have membership in cold. So we're going to have some contribution from mu open. And if temp is warm, then valve is half. So we know if it falls in here, we'll have some contribution from this membership function. And then we can go through the same thing that we calculated earlier, which is the minimum, maximum, etc. And if you do that, you wind up with these truncated, in this case, trapezoids, to get this overall output distribution for what our action should be. And we resolve that using defuzzification to get our final crisp output. So let's say we take the centroid and get this output value. And it'll be somewhere, in this range. I'll go ahead and say it's, 70% open or something. It's going to be something like that. And that's what our system will then decide to do based on those fuzzy input and output sets and our rules. And so that is a fuzzy inference system. You're not limited to only one input, but remember that the systems do scale rather poorly with the number of inputs if you have a rule base that uses conjunction. This is another example, but for car insurance. And so let's say you have two rules, and rule 1 says if age is young and car power is high, then risk is high. Well, that makes sense. It definitely makes sense that if you give a teenager a high-powered car, the risk of them doing something bad is relatively high compared to other people. You can also have another rule that says if age is normal and car power is medium, then risk is medium. We can then do the same thing with determining the risk for a particular person. So let's say that a person falls along this part of the age. So they're in between young and normal. And car power falls in between medium and high. So we can then take both of the active inputs for this rule, which are, age is young and car power is high. Then we know the output's high, but then we can see the contribution from each of these based on the minimum value on the input side. So we have this active output. The other rule that we have active says that medium should be active this amount, and then we have the combination of those into this aggregate. Then we can defuzzify that and find our crisp output value based on the contributions from these. Again, centroid or center of gravity is a very commonly cited method and does offer some nice properties, however, at the expense of computational efficiency. Typically, these are calculated numerically, and that can slow down the process quite a bit. Whereas if you can approximate the center of gravity somehow, or the more efficiently you can do that, the more efficient your calculations will be. Okay, so that is fuzzy inference systems very quickly. Before we move on, does anybody have any questions specifically on fuzzy sets, fuzzy membership functions, and the inferencing that happens within the system? see, I do see a question in chat. Is there a method to go about selecting membership profiles? Does that depend on my data? Do they give advantages depending on applications? So there's a couple different things to address there. The method to go about selecting membership profiles typically is done empirically, unless you're doing something very specific with trying to fit to data patterns and you're allowing that degree of freedom in your system where it can try to fit a membership function shape to the data like that. But typically how that's done is by fixing the membership function, depending on the properties it has, and then allowing the rules and the output membership functions to adjust instead. In fact, what you'll see in a really interesting talk next week, which is going to be given by Professor Jerry Mendel on explainability, is that he was representing fuzzy membership functions. He was trying to represent linguistic terms with fuzzy membership functions. And in that case, it does affect the shape because he had data points that he was trying to fit a membership function shape to, essentially, and also in the range. The other part of the question, do they give advantages depending on applications? Absolutely. So generally, in the literature, what you'll see is that triangular and trapezoidal tend to be preferred unless you need smoothness that the Gaussian functions can provide. And the reason for that is basically the simplicity in the interpolation, because absent of other information, a linear approximation of your data may be best, and it's probably the best place to start. So that is typically why triangular and trapezoidal are preferred. The downside to them sometimes is you get this mode switching where you don't have discontinuities, but you have piecewise continuous behavior, whereas with Gaussians, you get continuous behavior everywhere in the space. So that's one reason. If anybody has any other questions about membership functions, feel free to ask, by the way, but those are really good questions. Someone did ask, can we mix triangular membership function inputs with Gaussian outputs? Absolutely. You absolutely can. You can mix and match any way you want. Yeah. Really, the only thing that depends on is your software. There may be software packages out there for fuzzy that do not allow you to do that just because of how they're written, but there's nothing in fuzzy logic or in fuzzy inference systems that prevent you from doing that. It may make your calculations not so nice if you are writing that software, but it's not a problem though. In fact, what you'll see is people mix and matching input and output types to get certain properties. So if they want continuous things on the output, they may do Gaussians on the input side with something like a singleton on the output, so they can guarantee those properties, or something else. Yeah. So if there are no other questions on fuzzy logic, membership functions, or inference systems, I'm going to move on to the next part, which is much shorter, but deals with an important topic, which is fuzzy trees. So fuzzy trees, of course I'm having, there we go. Fuzzy trees are a way of combining a bunch of different fuzzy inference systems into a structure such that you can still approximate something without having the rule explosion that happens with a single fuzzy system. So in a single fuzzy inference system, the number of rules that you have to define increases exponentially with the number of inputs. And because of that, it is typically advisable to limit the number of inputs you have to a single fifth. But if you want to try to control or process a lot of different input values, you still need to account for that somehow. So a fuzzy tree is one way of creating a structure where you can still do that. So again, fuzzy logic has been hybridized and structured in many different ways. On the right, we have sort of a timeline of what has happened with specifically genetic fuzzy systems. But I wanted to highlight this because of what happened with fuzzy trees. So genetic algorithms, these have been around for a while, but these are inspired by evolution and survival of the fittest. They pair very nicely with fuzzy inference systems to create genetic fuzzy systems in order to learn the parameters of the membership functions, the rules, the output membership functions, normalization gains, all of that. There is a lot of stuff in the literature. It is very high performing, with the caveat that the number of inputs can't grow too large, or else the number of parameters that you need to define just becomes intractable. And genetic algorithms can be sensitive to the number of parameters, so the fewer parameters you have, the better. This is somewhat mitigated by cascading fuzzy systems. And so what you do here is, let's say you have 10 inputs, 10 variables that you care about. Instead of creating a single FIS, you may create a cascade of FISs where you have one FIS that feeds into the next and combines with a couple more inputs, et cetera, until all inputs are accounted for, but each individual FIS only has a few inputs. And then that was extended even further with a fuzzy tree, and this had no limitations on directionality. So you can have a bunch of FISs in the tree that are connected to any other FIS and so on. Whereas the cascaded system is this progression or almost waterfall type structure. Genetic fuzzy trees are this mass where you can have interactions between any of them. So this is a visual representation of a cascaded fuzzy system. Again, more cursor issues, I'm sorry. But we have this crisp data coming in, and this FIS that's at level 1 takes that data and outputs something. And level 2 takes the output from level 1, plus you might have other crisp data that's coming into level 2. And then you make a decision based on what the first FIS did, plus that new data, that other data, whatever it is. Then you output something and it goes to another FIS, which combines that output with potentially other crisp data. And then finally, this last FIS outputs the overall control action. So there's multiple levels. It's arranged in a hierarchy, and it can take the same states as a complex individual system, but the number of rules they have to define scales significantly better because each, I'm so sorry, each one of these FISs is only taking in a subset of the overall state information, the overall input data. It's not taking in all of it. The performance, however, is bounded from above by a single fuzzy system that takes in all the inputs. But typically in practice, what you'll see is that unless it's a very heavily, there are very heavy interactions between the variables, typically it can account for that. And by the way, this doesn't mean that you can't account for interactions at all, but it does mean that certain things that do have heavy interactions or dependencies, between the variables may need to be grouped together or more closely in that structure. If there is no coupling between those variables, the cascaded system can potentially have the same performance and with far fewer. I'm having all sorts of mouse issues. I apologize. The same performance can be maintained with far fewer rules, which is a big benefit. The complexity is lower. The optimization time is much, much faster to do that. To extend that, this is a graphical representation of a fuzzy tree. This removes those directionality and structural assumptions of the cascade. Feedback is also entirely acceptable. So let's say you had B2 right here. So this is at level B2, but let's say this is a particular FIS whose output then can potentially get fed back into B2. It can use its prior assignment to then update its next action. You can also hybridize easily with other elements. You could have, any of these be FISs in the tree structure, as well as something completely different. You could have a sub function that gets injected here that operates on some information that you're getting, including information from FISs, that then spits out other information to be used later. And again, removing directionality. So you can see A1 actually is outputting to both this A2 FIS and this B2 FIS. It could also input over to this other A1 or this other B1 FIS. We don't have those same directionality requirements that were in the Cascade. Again, performance is bounded above by a single FIS, taking in all crisp inputs, but really this offers you so many benefits by being able to deal with those interactions that the reduced rule base is extremely beneficial. Yeah, we've already talked about coupling and dependencies and variables. Yeah. Also, proper design must go into the structure of the tree to mitigate those couplings as much as possible. And whether that comes from expert knowledge, that can come from some learning process, some machine learning process. It can come from data itself, similar to how a decision tree is formed. There's a bunch of different ways to construct this. One of the quick and easy ways is if you have any domain knowledge, you can set a structure that the system has to adhere to. So this is a non-notional example of part of a much larger fuzzy tree, but we'll call this a fuzzy tree in itself. And this is from an air-to-air collaborative firing decision-making system as part of a broader air-to-air combat system that was developed back in about 2016, yes. And this has 15 inputs, but notice that no single node, in this case a node is a FIS, so all of these are FISs, and the blue is our inputs. And notice that none of them have more than 3 inputs, and the reason being is to cut down on the number of rules. Something of note is that a single FIS with 5 membership functions for each of these inputs would have more than 30 billion rules. So that is why having a single FIS take all the inputs in is really not tractable in this situation. And in this case, for explainability, the structure was set, I'm sorry, and mapped such that the subvariables are understandable. So what that means is that the subvariables that are coming out of each FIS actually mean something semantically. And what I mean by that is that they actually have a representation that means something with respect to the domain, the problem domain. So in this case, right here, what we have is target azimuth and platform 1 azimuth. And that is calculating effective azimuth 1. That is actually going to be the name of that output. And then we have another one calculating effective azimuth 2. And the overall effective azimuth is some combination of those. But then this effective azimuth, which actually means something with regards to, air-to-air combat, it's, an angle calculation. We can combine that with something else, a bearing differential, and then some sort of effective distance to then decide or give a rating to a particular strategy or tactic or whatever you want to call it. There's some potential thing you can do based on that information, which actually means something with regards to the problem. And you can create these structures through a machine learning process, but then you can potentially lose this explainability by having these combinations that actually mean something. And so this is just to give you an idea of what a fuzzy tree might look like for an actual problem and how you might want to start structuring things if you care about explainability, while also getting high performance and having a low enough number of parameters that you can optimize it effectively. So before I move on, does anybody have any questions on fuzzy trees? Okay. So next up, I'm going to talk about your milestone, which is an optional milestone, but we encourage everybody to do them just to make sure you're staying on track. And so I'm going to introduce this, and then Lynn, if you are okay, are we okay to do some code?
I am still working on some issues with my interpreter. I can
Okay.
definitely walk through the tipper example that SK Fuzzy has on their website, though, as a backup, if we think that's helpful.
Um,
No.
I'll I'll go through that actually.
Okay.
Yeah. I'll show that and then the code. So yeah, it's okay. So for the milestone, if you remember what Brandon showed last week when he was going over Asteroid Smasher, we have this class called Fuzzy Controller, and what you want to do is in init, which is the initialization of a fuzzy controller object, you want to create your object, create your controller, and you do that by defining all of the attributes for the fuzzy controller. And we'll see. I'll go through that in a second, an example of that. And then in actions, you want to use input data to be fed into your FIS, and then the output will uh, give some control value to ships, which is the interface for all of the ships. Whether that is, moving, turning, shooting, doesn't matter. Your goal is to simply get a fuzzy controller up and running inside of the environment using fuzzy controller. So this is just a quick example I made of a tree that is, it's notional in the sense that you might not use this, you might not have this structure. In fact, this is not a recommendation. This might not even be viable or perform at all for what you're trying to do, but it's just an example of a tree structure that you could potentially implement. So let's say that you want to get a firing decision, and in this case, let's just say it's a yes/no firing decision, or it's thresholded. And what you could do is you could take in some asteroid info, whatever that is. Maybe it's the nearest asteroid, direction, distance, etc., and you calculate a threat level, and then based on that threat level plus whatever your teammate is doing, if this is the multi-agent situation, you can then combine your teammate's decision, whatever they're doing, plus the threat level that your own ship perceives, and then have another fist that takes both of those in and decides whether to fire. So this is just a quick notional example. I'm not saying do this, um, but think about what types of inputs you're going to be using in your system and whether you need to do any pre-processing, because maybe for threat level you need to do something else, which is completely fine. Maybe you want to use some other process or algorithm to assess something or resolve something. That's absolutely fine to do that pre-processing and then feed it into a fuzzy tree. And then also, what are the outputs? In this case, we're just making a decision whether to fire yes or no. But in other cases, you might have continuous control, especially for things like, moving, um, your your turn rate, your uh, moving forward, backwards, all of that. And so that's where membership function things come into play too. Those shapes. So this is what you will be doing. Um, this is quote unquote due on October 4th, so 2 weeks. But really, yeah, you don't need to submit anything. Really, this is just to gauge your progress to ensure you can actually get this up and running. And so you're gonna make a fuzzy controller slash tree that's embedded in Asteroid Smasher, and it must consist of multiple FISs. They can be extremely simple. They can have a small number of rules, single input. That's fine. It's just to get it up and running. And you have to take in something from input data as an input to one or more of your FISs, and then you have to control some aspect of the ship or multiple ships based on their outputs. It can be the shooting, it can be turning, it can be moving, it can be all of them if you're a go-getter. But that is your goal for the next 2 weeks with Asteroid Smasher. Does anybody have questions on that before I move over to the code? Yes. Someone asked, can this be pre-tuning? Absolutely. We do not expect this to be optimized. You can just make up whatever rules and parameters that you want. It can be the worst thing that's ever been made as far as decision making. Like it can immediately decide to just run into asteroids. That's fine. Yeah, we will get to the tuning and optimization next time. Well, actually, after the explainability talk. But yeah, good question. Now, if you want to optimize it and do some hand tuning, like maybe you want to create one that has rules that actually make sense and performs well, absolutely, that will be very beneficial. But at this point, it's not a strict requirement. Yeah. Okay, so let's go take a look at the code. Brandon went over Asteroid Smasher last week. He also has it on PyPy now, so you can pip install and has instructions for how to do so. And if you're having issues with the repos or anything like that, again, put in the help section or discussion if you're just discussing how to do certain things. But if you specifically have questions for us in the help channel in Slack, yeah, feel free to ping us anytime. But after pip installing, you can access fuzzy asteroids. And so for fuzzy controller, which inherits from controller base, you're going to have init, and well, we don't have it defined here, but let's say you have init, and you want to be able to define all of your fuzzy systems parameters that are fixed. And then in actions, you want to be able to use that fuzzy inference system to take in input data and then output. So an example, let's say you're going to use skfuzzy. skfuzzy is a Python module. Oh, the site cannot be reached. Okay. skfuzzy is a Python module that does fuzzy logic. And you can make fuzzy logic controllers and inference systems. It's relatively easy. It's probably one of the better ones out there right now in Python. And also, this is not a strict recommendation. This is just one that's out there. If you have another one you would like to use, that's fine. If you want to write your own, that is absolutely fine. And in fact, for efficiency purposes, it might honestly be better. Scikit-fuzzy is not known for being that fast in evaluation time. In fact, it does things similar to the MATLAB toolbox, which uses numerical integration for defuzzification, which can make it very slow. However, as an example, I would go to the tipping problem, which is it's a classic problem in fuzzy control. And this is a problem that deals with how much to tip at a restaurant. You can read a lot about the problem, but really what I want to focus on is how you would actually implement this. So if we go down to the code, what they're doing is assigning, yeah, variables and membership functions. So we have quality, service, and tip. So these are the inputs, quality and service. That's why they're antecedents. And then consequent for the output, which is tip. In this case, they're auto-generating membership functions, which is fine for this example. You can do that too. Or I do recommend playing around with it to make your own, to define your own input sets. But yeah, definitely okay to generate them automatically for now. Later on, you will not want to do that though. And then this is defining membership functions that are being built interactively. So don't worry about the viewing. That's just so you can see what they look like. Then also they're defining the rules. So in this case, we have rule 1, which if the food is poor or the service is poor, then the tip will be low. So they're encoding this by saying the quality is poor or the service is poor, then the tip is low. Then we have another rule that says if the service is average, then the tip will be medium. And so we're simply saying if the service is average, then tip medium. And then the last one is saying if the food is good or the service is good, then the tip will be high. And we see, service is good or quality is good, then tip is high. So that is the encoding of their rules. And they load those into the FIS by creating what SK Fuzzy calls a control system, which is fine. You guys can use the same thing. And then they can evaluate it by doing this simulation. So what we would do, let's see if I can do this, is if we go up to where they're defining everything. So this is where they're defining membership functions, inputs, outputs, etc. You would put that in a init. You would define all these things in a init when you initialize your fuzzy controller object, along with your rules. So your rules are also going to be defined there. And then in actions is when you're actually going to take your object and evaluate it. Oh my God. My mouse wheel is possessed. I apologize. And so in actions, you would then have, let's say that you defined all of your rules. You have your membership functions, and your FIS is a function of rules and membership functions. And so you have this FIS object that's defined. In this case, you'll have multiple if you're doing a tree. But let's say you have, this one equals whatever their functions are. This is just basically pseudocode. Don't worry about these actual commands. You would be using the ones in SK Fuzzy. But then in actions, you would say, well, FIS1, I'm going to call that with, input data, whatever it is. If input data with a list, doesn't matter. You're going to take in some input data and get an output, and then you're going to, assign that to the output from that FIS or that tree. We'll just do that in one line. So let's say that you wanted to have high thrust depending on where an asteroid was. You could do this by creating a FIS that took in whatever aspect of the asteroid you care about is. So, maybe it's asteroid distance, direction relative to, your ship, etc. And, its velocity data. And then you can have one or more FISs that combine that information and give you an output to your thrust based on that. You could do that for firing bullets. You could do it for turn rate. Yeah, it doesn't need to be one single thing. In fact, eventually you'll have FISs and other things controlling all of the ship's behavior. So do we have any questions on the milestone, fuzzy systems, fuzzy inference systems, fuzzy trees, or the code? I did see someone commented that there's a fuzzy toolbox for Octave that can run MATLAB. I assume they mean MATLAB code with little to no change, but it has trouble handling inputs that are outside the range. Yeah, that can be a thing. That really depends on the module you're using and how it handles that. So typically what happens when let's say that you had an input value. So in our input, it goes from 0 to 25 for tip. Oh wait, we don't want tip. We want input value. So 0 to 10 for service. So let's say you had 11 as an input value. Not all modules will treat that the same. In fact, some of them may try to calculate an actual value based on whatever the membership function is doing outside of that range. which I believe is the default behavior for the MATLAB toolbox. And I'm not sure about skfuzzy, but one simple way around that is to simply normalize and bound your input space. So you can have something before that, do pre-processing that says, if input data or whatever it is, if service greater than 10, then do something like that to make sure that it's within the ranges that you're expecting. And normalization gains do tend to be a thing, but I highly recommend normalizing your inputs where possible or standardizing where possible. Okay, if nobody has any other questions, that is a wrap for today. But feel free to ping us if you have questions, especially about the code. Definitely Discord, or sorry, not Discord. Slack is the best place to go. And then email also works okay. But if you want to talk about things in general, also feel free to put stuff in the discussion channel in the Slack, which we encourage teams to do when they just want to chat with other teams about what they're doing, how to do things, interesting ideas, etc. But with that, we will go ahead and conclude today's seminar. Don't forget that next week we will have Jerry Mendel. He's a professor at USC giving a talk on explainability in fuzzy systems. He he gave a great talk at Fuzz IEEE this year, but he is one of the people on the forefront of explainability in fuzzy systems. And we'll be sending out an invite for that seminar shortly, by tomorrow, I would say. All right, thanks everybody for joining.